consider that one. So what we'll do is the statement of the property is like this. If DFT of x of n, so this is equal to the x of k, then what we'll get is then the DFT of x of n into omega into the power of minus ln. So omega into the power of minus L into n. So this is equal to the x of k minus L mod n. So this property is called as the frequency shift property. So where the shift in the frequency domain is equal to the multiplying the time domain content with the Twiddle factor or the exponential term. So in order to prove this one, we'll consider the DFT formula we'll consider. So let us consider the proof of this one. We'll consider the proof of this one. So what we'll do is, so x of k is equal to the summation n is equal to 0 to the n minus 1 x of n into omega into the power of k into n. So since in the proof we want x of k minus L in the x of k we want here, so we'll do replace k by the, so we're going to replace k by k minus L on the both the sides of the equation. We are going to do replace. So if you're going to replace, it has become x of k minus L. So this is equal to the summation n is equal to 0 to n minus 1 x of n into omega into the power of, in place of k we are going to replace with the k minus L into n. Now the LHS part will remain same. The Twiddle factor let us split here. So it has become summation x of n into omega n to the power of k into n into x of, that is, sorry, omega this one we can write it as, so that is x of k minus L is there. So we can rewrite this one as summation n is equal to 0 to n minus 1. So x of n into omega into the power of minus ln into omega into the power of k into n. So this in turn we can write as, so since here we can see the x of n is there, this one we can write as the DFT of x of n we can write here. So since x of n is the input, the corresponding the DFT will be equal to this one. Okay, so now, so similar to that one, the x of n into omega into the power minus ln is there. We can write this one as the DFT of, we can write as the DFT of x of n into omega into the power minus ln we can write. So that is the DFT of x of n into omega into the power minus ln. So this is equal to the x of k minus L. And since whatever the shift you are considering, it's a periodic, we can write like this. So this is the proof of this one. So similarly, we can write the other version, that is the DFT of x of n into omega into the power plus ln. So we can write as x of k plus L mod n, we can write here. So this is the other shifted version. This is the left shift in the right shift in the frequency domain, and this is the left shift in the frequency domain. So this is also, this property is also helpful now to find the DFT of the sequences, IDFT of the sequences. So we can take one problem and we can find out that one. So we'll consider one problem on this frequency shift property. So we'll see that problem. So the problem is very simple. Here, suppose if we know the sequence x of k, and we'll know the IDFT of the sequence x of k, we know. And if you want to find out the shifted version, let us do that one here. So let us consider the problem. If IDFT of x of k is equal to x of n, is equal to x of n. So this is equal to something called 1, 2, 3, 4 we'll consider. So 1, 2, 3, 4 we'll consider, and find IDFT of, we'll consider as x of k minus 2, x of k minus 2 mod 4. So we need to find out the IDFT of the x of k minus 2 mod 4. So this is similar to the frequency shift property here. The shift in the frequency domain is equal to the corresponding multiplication with the Twiddle factor. So in order to find the solution, what we'll do is, so the IDFT of x of k minus 2, we can write as IDFT of x of k minus 2, 4, we can write that one as, so as per the frequency shift property, so this is equal to the this term, so it is omega. So since it's a 4 point minus, in place of L we have 2 here, so it is 2 into n we can write here. Let us call this is equal to something called the new sequence, which is called y of n here. So we'll do that one. So we'll find out the sequence. And also we know omega 4 to the power of 2 is nothing but it's a minus 1 only. So we can rewrite that one as y of n is equal to x of n into minus 1 to the power of n we can write, because omega 4 to the power of minus 2 is because we know that omega 4 to the power of 2 is equal to minus 1. So let us substitute n is equal to 0, 1, 2, 3. So n is equal to 0 means y of 0 is equal to x of 0 into minus 1 to the power of 0. So x of 0 is 1. We'll get the same. When I substitute n is equal to 1, so it has become y of 1 is equal to y of 1 is equal to, so it's x of 1 into minus 1 to the power of 1, so means will become minus 2. So similarly, when n is equal to 2 is there, y of 2 is equal to, so x of 2 into minus 1 to the power of 2, so we'll get the same 3. And similarly, when I substitute n is equal to 3, so it has become y of 3 is equal to x of 3 into minus 1 to the power of 3. So this has become minus 4 will get. So therefore we can write the sequence as y of n is equal to 1, minus 2, 3, minus 4. So like this we can find out the IDFT of the sequences without knowing the corresponding terms. So usually the properties of any transforms will be helpful in order to reduce the number of calculations, mathematical calculations.